So we're looking at chapter 18 on ketones and aldehydes, part 1. Classes of carbonyl compounds. We have ketones, carboxylic acids, esters, as well as aldehydes, acid chlorides, and amides. In terms of the structure of carbonyl groups, carbon is usually sp2 hybridized, and you have this C double bond O with the dipole moment going in this direction. The C double bond O is shorter and stronger and more polar than a C double bond C bond in terms of alkenes, as you can see shown here. It exhibits resonance, in which your major resonance form is shown here, and then your electrons from your double bond can go to the oxygen, generating this form where you have charge separation. So the carbonyl carbon here, in this case, has a partial positive charge, which will react as your electrophile. In terms of ketone nomenclature, you want to number the chain so that the carbonyl carbon has the lowest number, and then you replace the alkane E with -one, indicating the ketone. So in this case you have 4, which would be butanone. So it's at the 2 position, so it's butane 2-one. Here would be 5, penta 3-one, and it's 2,4-dimethyl, and here's 1, 2, 3. Propanone, so propan 1-one and 1-phenylpropanone 1-one. In terms of cyclic ketones, the carbonyl carbon is assigned number 1. When the compound has a carbonyl and a double bond, the carbonyl takes precedence. So here's 1, 2, 3, 4, 5. So it's cyclopentanone at the 3 position, 3-methylcyclopentanone. Here's one with a double bond. So it's cyclohexanone. It's a cyclohexene. So it's at 2. The ene, so it's cyclohex 2-ene 1-one. Here, 1, 2, 3, 4, 5, pentanone, or whether it's at the 2 position, so it's pentane 2-one, and at the 4 you have 4-methyl as well as 4-hydroxyl. Aldehydes nomenclature, the aldehyde carbon is number 1, and then you're going to replace E with al, and if the aldehyde group is attached to a ring, the suffix carbaldehyde is used. So here's 1, 2, ethanal, right? This is 7-mer. Heptanal, in which you have at the 3 and the 4 position a methyl and a bromo, so it's 4-bromo 3-methyl heptanal. Butanal, and 3 position is a hydroxy group, so it's 3-hydroxybutanal. This is a pentanal, and at the 2 position is an ene, so it's pent 2-enal. This is cyclohexene, carboxaldehyde, right? Here, this is a carboxaldehyde, but it's cyclopentane, 5-mer, 2-hydroxy, 1-carboxaldehyde. In terms of a carbonyl as substituent, on a molecule with a high priority functional group, a ketone is an oxo and an aldehyde is a formal group. That's important. Oxo and formal. Aldehydes have higher priority than ketones, so aldehydes will be a priority over ketones. So if we look at examples, this has both an aldehyde and a ketone, so the aldehyde will be the priority, so that's going to be the parent. And then the ketone will be known as oxo, so it'd be 3, right? Oxo, pentanol. Here you have acid and an aldehyde, so your parent becomes the carboxylic acid, and your aldehyde will be known as the formal group. So here's 2-formal benzoic acid. Parent is the butanoic acid, and there's 2 of these, and this is 3 for dioxo butanoic acid. In terms of common names for ketones, you're going to name as alkyl attachments to the carbonyl, and you're going to use Greek letters instead of numbers. Here's ethyl group, here's methyl group, and it's a ketone, so it becomes methyl ethyl ketone. This is a sec-butyl, this is another sec-butyl, so it's a di-sec-butyl ketone. Here's isopropyl group, here's an ethyl group, but at one of the sites you have this bromo substituent, so you're going to use Greek letters, so this is alpha, this is beta, as you're going farther away from the carbonyl. So it's beta bromo ethyl isopropyl ketone. Here you have a tertiary butyl group, as well as now you have a propyl group, but at this position you have a methoxy. So again, you're going to list as alpha, beta, gamma, going from left to right from off the carbonyl. So it would be alpha methoxy, propyl, tert-butyl, right? So it's tert-butyl, alpha methoxy propyl ketone. Historical common names, this is known as acetone, acetophenone, propionone, benzophenone. Here, this is okay, the parent is the aldehyde, alpha, beta, gamma, right? So beta bromo butyraldehyde or 3-bromobutanol. Here is 1, 2, 3, so it's propionaldehyde. At the alpha position is methoxy or 2-methoxypropanol. Boiling point. So ketones and aldehydes are more polar, so they have a higher boiling point than alkanes or ethers. They cannot hydrogen bond to one another, so their boiling point is lower than the alcohol. So they have higher boiling points than the alkane or ethers, but lower than the alcohols. If we look at solubilities of ketones and aldehydes, they're good solvents for alcohols. Lone pair of electrons on oxygen carbonyl can accept hydrogen bonds from OH or even NH. And acetones and acetaldehydes are miscible in water, as you can see here. Formaldehyde, right? So formaldehyde is shown here. They're gas at room temperature. Formalin, when you add water, you produce formalin, is 40% is a 40% aqueous solution. Trioxane is a cyclic trimer of formaldehyde, right? That you can take trioxane and when you heat generates formaldehyde. And this is paraformaldehyde, which is a polymer of formaldehyde that when you heat up generates formaldehyde. So if we look at the UV spectra of conjugated carbonyl compounds, conjugated carbonyl compounds have characteristic pi-pi star absorption in the UV spectrum. Additional conjugated C double bond C increases lambda max about 30 nanometers, and additional alkyl groups increases at about 10. So if we look at propanol, right, you have lambda max of 210 due to the conjugation right here. Now, as you're adding alkyl groups, you're increasing it. There's about 3. You're increasing it about 30 nanometers to 240-ish. And now, if you're adding alkyl groups, in this case, due to the ring, this is also adding 3 alkyl groups. Again, going slightly higher than over here, 244. If we look at electronic transitions of the C double bond O, right? So you have a pi, and you have your pi star, right? So pi, they're on the same side. Pi star, they're on opposite sides. And there's an allowed transition. So they have small molar absorptivity. If we go from here, where you have this non-bonding orbital into pi, so n to pi, the n to pi is forbidden. This doesn't happen. So an important thing to note is that carbonyl N-to-pi absorptions are very weak and are often obscured by stronger absorptions. Therefore, they're rarely useful as the pi to pi star absorptions. Industrial importance. Acetone and methyl ethyl ketones are common industrial solvents. Formaldehyde is used in polymers like Bakelite and many other polymeric products. Also used as flavorings and additives for food. Some just examples of aldehydes and ketones in foods. Butyraldehyde, right? Vanillin, acetophenone, trans-cinnamaldehyde, camphor, pyrethin, carvone, and muscone. They're used in all these different things. So Grignards can be reacted with aldehydes, or shown here. And when they do, as we've seen before, in the presence of protonated water, will generate an alcohol, right? The secondary alcohol can then be oxidized to form the ketone, so that you can go from aldehyde, alcohol to ketone. You can take primary alcohols, right, and then oxidize them with various reagents, PCC, you've learned about, sworn, DMP, to the aldehyde. So this will, PCC will selectively oxidize primary alcohols to aldehydes. Sworn as or DMP can also be used, and it doesn't over-oxidize to the carboxylic acid. Ozonolysis, you can use ozonolysis to generate ketones and aldehydes, right? So if we have, for example, this molecule here, this will generate an aldehyde and ketone, right, accordingly. And you can use Friedel-Crafts reactions to generate ketones. So you can use an acyl chloride, right, with benzene or modified benzene structure in the presence of aluminum and water, generate your ketone. Again, depending on what group you have, this is para and ortho, are activating. If G is hydrogen, an activating group or halogen, you're going to get this. And you can hydrate alkynes, right, using oxymercuration. So in this case, mercury and sulfuric acid and water. This will generate an enol, which then will rearrange to the methyl ketone. And so here's an example. Again, when you oxymercurate, you get the enol, and then rearranges to the ketone. Initial product would be, right, you have Markovnikov addition, right? And then the Markovnikov addition will then tautomerize. So internal alkanes can be hydrated, but mixtures of ketones often result. So you want to make sure you use terminal alkynes. Hydroboration, right, of alkynes, you're going to use thiaborohydride, peroxide sodium hydroxide, again, generate the enol, but this will do anti-Markovnikov addition, generating the aldehyde. So you want to use terminal to generate the aldehyde. So how would you synthesize, as a question, each compound from the starting materials containing no more than 6 carbon atoms? Here's A and here's B. So for A, you can use Grignard reagent of the phenyl Grignard reagent and then your aldehyde, right? This will react in ether and solvent in the presence of protonated water will generate your alcohol, right? And then you can oxidize to finally get to the target. So another way to generate that same product is to do Friedel-Crafts acylation, where you start off with your benzene, your acid chloride in aluminum trichloride to generate your product. In terms of compound B, you can start off with the the cyclopentane-bearing Grignard reagent. In the presence of epoxide, open up the epoxide so you generate the alcohol, right? And then oxidize this to the aldehyde using a mild oxidizing reagent, PCC, sworn DMP, to generate your target. As an alternative, you could have used this alkyl bromide reacted with an alkyne, right? So this is your nucleophile, attacks, kicks this off, generating your alkyne, then using hydroboration of the alkyne to get to the aldehyde. So there are many routes to actually generating the product. If you want to synthesize ketones from carboxylic acids, you can take carboxylic acid, phenolithium, which we've seen before. This will react two equivalents, right? Kicking this off to generate the dianion. And then in the presence of protonated water, well, it'll protonate these, generating the hydrate, and then water will eliminate, so your electrons from your oxygen will come down, right? This will kick out, and then also then the OH minus will then pluck off the hydrogen to generate the ketone. So organolithiums will attack lithium salts of carboxylate anions to give these dianions, and then protonation of the dianions form hydrate of a ketone, which quickly loses water to give the ketone. So ketones and aldehydes can be generated from nitriles. Here's an example. First step is your Grignard reagent, which are shown here mechanistically, forming this magnesium salt of an imine. Then you have a replacement of the magnesium salt with your proton, generating the full imine. Once the imine is generated, it'll react with H3O+, plucking off the proton, the rest of the electrons going to the remainder, so that you generate something that looks like this. NHH. Sorry, please bear with me. Here, I'm not going to draw out the rest of the R groups. And then you have water come in, and that's going to attack your electrophilic carbon center. Electrons go to the nitrogen. Sorry, I'm going to have I have to redraw some of this. Carbon, nitrogen, H, right? And now you have OH, plus. Your electrons from this nitrogen will pluck off electrons your proton from that water that has attacked. And then, I'm sorry, you're going to have to deal with me here. Then you have NH3, right, which is a good leaving group, and then you still have OH here, right? So your electrons from your oxygen will come, form the double bond, kick these off, and again, bear with me here. You have this OH plus, right? And then your NH3 is still in there. Will come and pluck off that hydrogen, generating the neutral product, which is here. Sorry about this, guys. All right. So you can take nitriles and reduce them into aldehydes using a reducing agent like diisobutyl aluminum hydride, shown here. And the first thing that happens here is you have here I'm going to draw it as best as I can. AlIBu. Sorry, that's Bu2. So you're going to have this happen, right, where your electrons, your hydrogen goes on one side, your aluminum diisobutyl group goes on the other side, and then your electrons from your nitrogen will pluck off a hydrogen from H3O. Now you're going to generate, sorry about this, it's going to look messy, but hopefully you can see what's going on. Here's your protonated version, aluminum, and I'm not going to add the isobutyl group, but that's over here on one end. And so here's what you have, and then you have H2O, right? That remains because you've deprotonated. So here, sorry, here's your H2O. Electrons will attack your electrophilic carbon center, go to the nitrogen, and so then you'll have nitrogen, hydrogen, here's your aluminum complex, here's your OHH, electrons from your nitrogens, plucking this guy off, now you have electrons on your oxygen, right? So this will have now your OH, nitrogen, hydrogen, NH2Al. Sorry about this, guys. Hopefully you can see it. So now your electrons from your oxygen will come down, right? This will go over here, generating your almost aldehyde, right? But you have it protonated, and your NH, so it's NH, pluck this off, quench the positive charge to generate, again, your aldehyde. It's a bit messy, but you get the point. So the first step is a reduction with dibial, and then protonation with the H3O+. These are aluminum hydrides. Diisobutyl aluminum hydride is commonly used for nitrile reduction. Aldehydes can be generated from acid chlorides. You can take an acid chloride, and you can take lithium tritert butoxyaluminum hydride to essentially replace this chlorine with a hydride. It's essentially a milder reducing agent and reacts faster with acid chlorides than with aldehydes. Lithium dialkyl cuprate reagents, shown here, as also known as Gilman reagents, can react with acid chlorides and essentially generate the ketone. This will just essentially transfer one of its alkyl groups, important, to the acid chlorides. Grignards and organolithiums cannot do this reaction, right? So keep that in mind. And then nucleophilic addition, so you can look at, here's your ketone. Nucleophile will come, attack this carbonyl, right? It's partially positive, so electrons from that pi systems go to the oxygen, generating the alkoxide, and then that will protonate, right? So let's show that the electrons will protonate, generating your product, which is the alcohol and your nucleophiles. So in general, aldehydes are more reactive than ketones, and we'll stop here for part 1.